I'm going to do a whistle-stop tour, so hopefully you can get the presentation afterwards. So I might go quite quickly. Just to give you an intro, I'm Associate Director at Flanagan Lawrence, an architecture firm that's been around for about 3.5 years. We've got about 80 employees. We've won a few awards. This is one of our projects that was in the Olympic Park, which was an acoustic performance stage. We do a wide range of workflows, super prime residential, interior design, and cultural work. And we're actually part of a group, so we have an interior design company. We also have an R&D company which I lead, which basically mainly just mucks around, basically. Okay, we have all eaten, which is great, but you know, there's always something, a different flavour for everyone. So let's just think about what we use Dynamo for at Flanagan Lawrence. We use it for form generation, we use simulation, optimisation, and data migration. There will be a degree of crossover with what Lawrence has demonstrated to you, which is a really great presentation, I might add. So hopefully it will be tying up nicely with some of the stuff, practical applications that we've used. But basically, in a nutshell, any visual programming is basically flowcharts. That's all it is. PowerPoint's very good at flowcharts, I might add. But they're a bit boring to look at. Even when you saw the Dynamo ones, they're a bit kind of... So I prefer to think about what the ingredients are and what the outcomes might be. Sometimes it's more about thinking about what the question is rather than necessarily what your outcome will be, because if you try to define what your outcome will be too much, then sometimes you end up with something which is what you would have got anyway without actually trying to do a really clever process. What essentially Dynamo allows us to do is try and sort some of these ingredients. And sometimes when you add other variables in there, you end up with different answers. Sometimes you get Hawaiian pizza, sometimes you get pepperoni pizzas. The thing is, what Dynamo allows you to do is allow you to think in a way that you can't necessarily do yourself. You might think linearly about how you're going to tackle a problem, whereas if you want to kind of create some kind of Dyna pizza, you might end up with a whole host of kind of smorgasbords of flavours and a really complex thing that you couldn't previously have thought of yourselves. And that's really why we started using it as a tool ourselves in our practice. So if we get on to form generation, this is one of our projects, the Acoustic shells, which is down in Littlehampton on the south coast. It's 2 concrete shell forms, and we started in about 2012, and we used a very, very early version of Dynamo to basically go, oh, let's see if we can make the shape, because you can't draw that shape in Revit. That was how we started. But quickly we realised that we could actually use it to try and explore the acoustics of the shape. What we're using here is a ray bounce tool, which effectively bounces a single sound source off the surface so that we can start visualising whether the shape was actually good for a performance. So rather than just totally relying on an acoustic engineer to validate design, we start to have an iterative design process with acoustic engineers, because we're visualising something that we like as architects, but also there's some kind of grounding in terms of the way that they're thinking. But we also discovered that we could be using Dynamo to help the fabrication of it, because this is a double spline curve surface which has no consistent thicknesses, and is made by, believe it or not, Shotcrete, the company that does emergency repairs to motorway bridges. It's a bit unusual for them. What we discovered was that we thought of a really clever way to architect perfect desktop solution for how to fabricate something, and when you got to site, that method doesn't work because actually the site's wobbly and people don't necessarily understand what you're trying to do. So what we did was we actually laser scanned the formwork scaffolding that the fabricators had put up, and then rebuilt that inside Dynamo so that we could understand where the actual bits of scaffolding poles were crossing over the form that we had. Then, first Revit shot for you, actually itemised all of those individual pieces of scaffolding, and that's the outcome. See, it's almost like a random selection of interfaces inside the surface, but we had a surface variation of less than 2 mil outside of the original design intent. So that meant it performed structurally, but it also performed acoustically, which was much more sensitive than the surface quality than the structural thing did. Essentially, we only had 100 grand to build this, so the limitation of this design was actually the volume of concrete that we had. So although there was all of these other constraints we worked with, the computational aspect of Dynamo became extremely useful for us, in allowing us to design something which we never would have been able to think of, frankly. So, simulation. Well, that got us thinking, how can we start using computational design in order to help us understand complex acoustics problems, have a better conversation? We started thinking about time intervals and reverb. This is just an illustration of actually thinking about multiple sources inside a box and how complex that bounce is. Fortunately, we had a project to apply this to. This is a theatre which is hopefully going to be built in Wembley near the stadium. The stadium's just in the background there. This is the foyer area. It's about 100 metres long, and it's going to have a collection of uses simultaneously. But the client was really keen for them to have a completely open space. So therefore, there are different acoustic qualities in the space, but you want to have some kind of unitised ceiling arrangement with different noise levels and different levels of quietness and loudness. So what we did was we built the whole thing in Dynamo and started to do some computation based on our notions of how much sound was going to be in here. This is close enough to 1 million calculations. It took us about 6 hours to run through a machine, possibly a little bit over the top, but it allowed us to start to really have a comprehension of how complex the bouncing of multiple sound sources inside a single space was going to be. What we realised, however, was that because, and as mentioned earlier, that you can start to use C# inside Dynamo, you can actually improve the processing time for multiple complex stable calculations. Essentially, this is something we just found on the internet. It's a multi-threading algorithm. You can build that inside a node, inside anything that you're doing for an optimization, and you can just run your processes considerably faster. It will use all of the cores on your computer rather than just the single core that Dynamo will traditionally use. What that meant was that we then able to do a series of analysis results and this, graphic visualizations of the surface perforation amounts that we needed into every single panel inside this modular ceiling system. And then we subsequently created another script which then positioned all of the perforations on all of the ceiling panels. Then we used some Revit adaptive panels to rebuild all of that. And then we laser cut all of the ceiling panels. So essentially that process from testing all the way through to fabrication was done pretty much inside Dynamo and Revit. And that's just using some people like myself that I'm not an experienced programmer. I don't know loads of coding language. It was just thinking about what the problem might be and then just allowing the software to kind of explore ideas. So this is why we really like this software and why you can apply it to all manner of host of problems you might potentially be having. Optimisation, however, that's when we start to need to get the mathematicians involved. So this is the Greengate Embankment project, which is currently number 101, is pretty much approaching completion. So this is just on the Salford border. I don't know if anyone's familiar with this project that's being built. Basically, the 101 building, it's there. The 101 building is a square. It's pretty simple. But because of quite a complex arrangement of site boundaries, the building 100 ended up being a 7-sided shape just to try and achieve the floor areas that we needed on the project. But it's constrained by the listed embankment facade. What that meant was that it became an excruciatingly expensive building for no apparent benefit. See, at a design stage, we used adaptive panels again just to develop some kind of facade system, which we applied to both buildings. But the difficulty was, this 7-sided building meant that we had loads of custom panels, making it prohibitively expensive. So the client went, okay, I'll build the square one, but I'm not building this because this is way too expensive. This is just stupid. So the challenge to us was say, okay, well, how can we use some of these skills that we've been using for these double curve shapes to actually apply to a kind of sensible building and have some efficiencies? So what we did was we built that geometry for a single floor, obviously it repeats, inside Dynamo, so that we could establish what the constraints were. Obviously the first thing, it has curved corners, and we realised that that actually had no bearing on the standardisation because curves were always going to be specials. So we took those out. Then we introduced something called PythonScript. Now, the reason why we use PythonScript is because PythonScript allows you to do recursive functionality. It allows you to do loops. Now, the caveat to this is a project that started before you could do looping in DesignScript that you can now subsequently do. Some of these looping processes just direct inside Dynamo. So this is by no means, this is not the only way in which you can do this, but this is how we did this. So we built the definition of the shape, the points that controlled it. Then started to create a class. So just a quick show of hands, has anybody used Python before? Good. Just David in the back. So basically, you create a series of small little definitions. Basically, if you keep your eyes peeled, the text in green, essentially to a degree, is a bit like a node that you've been seeing in the canvas beforehand. So textual language is inherently much more complex, but what they're encapsulating is a very similar thing. So class facade basically is just basically a big node definition saying this is the facade of the building. And essentially, for us to optimize it, we created something called a particle spring system. So we define the particle, that's the corners, 7 corners. Then we say, okay, well, between every spring, so every length of facade, there are 2 particles holding them. And then the facade is basically contained between all of those 7 springs. So if you move one spring, that has an inherent effect of moving all the other springs around the circle. So you essentially create a 7-dimensional problem. So you can't do that by hand. It just becomes too complicated because you're just chasing your own tail forever. So we actually found, the first time we ran this, that there was no convergence. We couldn't actually get a solution because the learning rates that we defined inside this were not incrementally large enough. Basically, we weren't actually being brave enough to try and explore different geometries, different setting out of these points. So the great thing about just doing iterative programming is that you just tweak some numbers and tell the computer to go away and do all the hard work for you again. We increased the learning rates, increased the number of iterations, and then we got convergence. This curve here is a fitness function, which is similar to these other watch nodes, but this is a watch 3D, so basically it's allowing you to kind of visualize data in a graph form. Essentially saying that there's a convergence at the bottom there. It's saying that actually it's achieved a point where we wanted to achieve some kind of efficiency. And what was this efficiency that we're talking about? Well, we just wanted to have one panel size. It's just as rational as that. We just wanted it to move the 7 points around until it ended up with only 1,500 wide panels, and thus saving, well, approximately £2 million on the build, because it was a very expensive facade system anyway. And now they're going to build it. As simple as that. So rather than spending huge amounts of time trying to work something out by hand, actually we just tackled the problem differently and used computational design to try and solve something and demonstrate to the client that we really did understand what we were designing, which is often a struggle for architects. So, moving on to I said I was going to go fast, sorry. Moving on to even more complex problems that we started to think about. We started to say, okay, well, that was still a relatively controlled process that we were doing. What happens if we're really trying to bring in multiple sources of information and also multiple solutions? It's still manageable when you're just moving 7 points around. You can still use a conventional linear piece of coding. When you want to do multi-objective optimizations, however, you need to start thinking in a totally different way about saving time, because that last optimization still took 80 iterations to go through. You need things to start cross-evolving and randomization to occur. So we used a node which is called Optimo, which I encourage everyone to download and also play around with, which is freely available on the Dynamo BIM website. And what that allowed us to do is to start having kind of notional optimal choices that have cross-evolved with each other. Well, how's that useful for us? Well, we started to think, okay, well, if we're going to design and demonstrate that we're acoustic experts, how about having multiple different performance requirements in terms of single performances, big and large spaces, amplified, unamplified. How will that actually affect the surface geometry that's going to be used to reflect that sound, and how big those audience might potentially be? Essentially, we can add in multiple levels and layers of information and evolve answers, so that we can then essentially be given an existing site, an outdoor theatre in Poland, which basically didn't perform very well and was subject to all manner of kind of environmental things. We were able to evolve a roof which massively enhanced their performance quality. Just doing, essentially 5 iterations. So rather than it taking us hours to calculate results, like I showed you with the earlier acoustic ceiling solution, we're now doing it in minutes to get actually optimized solutions for our designs. And we're so confident, actually, this was a competition. We won the competition because we'd already got the answer before anybody else had even suggested a notion of what to do. We said, well, this works. There you go. And that really has kind of fundamentally changed the way we work as a practice. That we can, as I say, bring together all the parameters and start saying, okay, how do I completely reshape the problem and start to solve things differently? Now, data migration, the least sexy of all the things in the world. BIM Level 3, had to get it in there. Dependency analytics, that's the bit that's kind of interesting to me again, the bit where it starts to get kind of interesting, because we've got all these other reams of data that are coming in, and if we kind of just consider it only purely as data and nothing to do with actually some guy with a hammer on site, then it is actually there is actually a great deal of similarity between these acoustic problems I'm talking about and some of these big kind of BIM Level 3 problems that we're trying to kind of resolve. But as we all know, to get to BIM Level 3, we need to get to BIM Level 2, which we haven't. But we need to become kind of data agnostic in order to do that. So, as mentioned earlier, Dynamo is one of the ways in which we could be doing this. Rather than buying closed-off siloed pieces of data generators, why not just use a tool that kind of just scavenges from all of them and moves data around? That's what we were thinking. So I'm going to apply. So we apply this to a typical project. We were very lucky that we had an architectural appointment, but also our Innovate company was employed to be the information manager. I think we just said it was a good idea, and they said why not. It's so many projects you were doing stuff like this. The client says, I want BIM Level 2. I don't know what that means. Everybody worked really hard, and we have a building with 360 apartments, and it's all mostly done in Revit. There's 60 models. It's all working in that workflow, and this is actually the reality of what BIM Level 2 is to kind of clients. Some spreadsheets and pipes going through sinks. That's basically what they're kind of doing, and that is extremely laborious from an information manager point of view, because actually we're not adding any value whatsoever to the process. We're just kind of going, oh, that's a bit wrong, and then repeating it infinitely. So, the initial workflow was cool for us. That was fine. There was 3 Revit models, and we used Navisworks. That's fine, nice and easy. And then just did an Excel report. However, then we get up to 60 models, and we've got hundreds of thousands of clashes, and we still have to turn that around in the same amount of time. It becomes ludicrous and totally unmanageable. Something you thought was completely fine as a start point is actually not workable. So let's use Dynaworks, which is another free one to download, and that basically allows you to optimize and run all your Navisworks clash reviews and get it all done for you. So we do batch importing. We can arrange 60,000 clashes and get them to run all by themselves in 6 minutes. Essentially, it's very similar in terms of this file path stuff. In fact, we even run it in silent mode. We don't even open Navisworks. It just runs by itself. It sorts itself into the various preloaded, imported filter sets that we want them to do by the active and etc. The standard Navisworks things, if you're familiar with it. And then that goes straight into our Excel reports and straight into our automated trackers. So we went from, oh God, I'm going to take 6 weeks to do every single report and I've got a 2-week turnaround, to I'm actually doing them in about 20 minutes, which is considerably more profitable, I might add. And the clients, when you say that to clients and say, I'm actually doing this quickly, they're going, well done, you're clever. They don't go, oh, well, I want that for less. They say, well, that was why I was paying you in the first place, because you're doing it, you're helping the process. But we thought, how can we help it better? Because we were looking very clever and very smug in these meetings and saying, resolve 20,000 clashes you. And they were going, well, I don't know where they are. I'm using Revit. So we said, well, surely we can ship that back again. And, well, Auto-Section Box, which was, just in the regular API, it is now. We just thought, okay, well, you can just grab those IDs and pump them back in again. So that's exactly what we did do. We used a bit of Python to access the API, out it goes in terms of just element IDs, and just creates views with section boxes around the clashes of the two items. It's as simple as that, really. It saves a lot of time in terms of there's still some person who has to do this work. There's some person kind of underneath a kind of reams of paper just slowly ticking things off. And suddenly we found a mechanism where actually there is a labour saver for actually resolving these problems. Final one, I'm really motoring. I'm doing quite well. Final one I wanted to kind of show you was just my pet peeve about phases in Revit models. They don't like to talk to each other. In fact, they tend to make Revit explode. So what we did find was, for example, if you're doing a schematic stage model and also a detailed model simultaneously for different purposes, you might want to be able to migrate information, make rooms aware of themselves. If that makes any sense. You've named the apartment 612, and you want all of the actual rooms inside that apartment aware of the fact that they're in that apartment. It seems pretty much a no-brainer, but because they're phase dependent and can't be in the same space at the same time, they can't do that. So essentially what we're doing is just pulling information saying, are you in this space? Find them, then locating that space, and then pushing them across between each other. So that's just a kind of another example of some of the stuff that Lawrence was talking about. That actually, the bread and butter workflow, the stuff that actually just takes some poor soul just hours, just going through 360 apartments multiplied by an average of 7 rooms per apartment, just renumbering. It's just so tiresome for them. Whereas we can just run a script and away you go. One thing I would say though is that make sure that you've got your work sets properly filtered before you run this script, otherwise you will corrupt your files. So we learned that. Just be careful. And then the remapping goes through their apartment data migrated back in. There it is. It knows where it is. Filters set up. And then we started realizing that you can do things where you've got items that are bridging multiple phases, so they can start compiling the information from multiple phases. So, for example, a door can pull the to from data from one phase, and it can pull the apartment number from another phase, and there's no problems because you're just using Dynamo to kind of circumvent these problems that you might previously have been having. The benefit of doing that is when you're starting to export IFC. So I go back to that whole level 2 stuff. They're expecting IFCs from us, and where the rooms themselves are entities, and you might be exporting rooms within rooms because you've got an apartment and you've got rooms, and you're using someone's using Celebri to say you've done it all wrong. It allows you to have some kind of upstream thought process in how you're putting data in and out of various vessels in an IFC space. Where that's ended up is, go back to that pizza analogy, is the bit that everybody hates, is ANCHOVIES, COBie. And basically, 700 fields, a lot of this is coming from disparate sources. Where we're working at now, and I'm afraid I can't zoom in on this one, is that we're pretty stable in terms of a stage 4 deliverable. We've got unit class, we've got all that kind of data in the first 3-4 tabs of COBie, because that's stuff that's kind of design teamy stuff, that space allocations and all these things. When you get to the system and the product level classification, that's stuff that's coming from people that don't know anything other than, say, Excel, and they've heard of Excel, they can't even use it themselves necessarily, and that's not me to kind of be insulting, that's just because their trade doesn't need them to know any of those things. they do have data sheets, they've got all these things. Actually, what we're doing is we're working with about 50 trades simultaneously on this job to compile data that we've extracted and formatted in a COBie format to them. And then because we're able to use Dynamo, we're able to script that in to several thousand items inside our models and be confident that because it's being done in a very structured way, that process is essentially a self-validation of the way that it works. So you can imagine this is basically scalable. You can apply it to across multiple models, you can apply this to multiple supply chains and allow you to kind of feed this in so that you can get some kind of standardized COBie output, which is basically kind of magic to most people. But actually we think it's not. It's actually a lot simpler than most people thought it was. Amazingly, I went faster than I was meant to. I don't know how, but that genuinely is my last slide. Thank you.